Okay. Well, thank you for the invitation. I know I'm following a long list of high-profile speakers. I'm honored to be here. I'm not the director of the Texas Health Science Center. That's too big because the South. And that's 4 years ago when we started. And the overall framework of predictive modeling using EHR is basically from EHR data. We use so-called static embedding. We translate those individual medical code into a bunch of numbers, and that's more digestible for the neural network. And we use a prediction engine, basically another neural network taking those numbers in and then predict the outcome of interest. We have been working on this for a good 4 years, and we have developed a number of methods and tools around this. This suffice to say, we sort of make this process much more complex, but also more richer. And today, we are going to share two topics. One, Med-BERT, is a contextualized embedding, and also a covariant published early this year for predicting COVID-19 outcomes. The work is largely done by amazing student Laila Rasmi, now a assistant professor in my school. So Med-BERT is we started actually just after the publication of the BERT model, but it takes some year and a half to actually to finish the project. So what we did, let me show. The idea is that in AI everywhere, there is notion of a foundation model, namely some big neural network model. It can take in any data modality. It can be text, NLP, image, speech, structured data, 3D signal, or whatever. And through some training, it can embed everything into this this model, and then from it, you can fine tune to generate to do any of the tasks. So so it's almost like a general model, like a human. It's because it sees different modalities as like similar things, because inside those foundation models, those are numbers, they are embeddings. So the architecture of such foundation model is namely the transformer model. It is started about five years ago, but little has changed since its invention. So the model looks like a bunch of layers, and each layer has a self-attention and then a module of memory. So and then it will repeat itself number of times, and then translating a bunch of tokens into another set of tokens. It sounds generic, abstract, but it's really a general scheme to modeling all diverse kind of data. So what Med-BERT does is basically using this transformer model. We take in the electronic health record data. It's structured but little sequence, so it's not the exactly same of any other data modality, and we inject that data into this transformer model and to predict to embed that data into some sort of contextualized embedding, and then can be used for downstream prediction tasks. So we show that when we pre-train this model, we use some 28 million patients data, and after the training this model, and we can augment any small anybody has a small local data. You don't have to have the 28 million data. You can just using your own data, and all you need to do is fine-tune this pre-trained model with a few iterations using your own prediction head, and you can make a better model on the other side. So we show that, for example, in a heart failure prediction for diabetic patients case, we compare, say, this is logistic regression model, which is sort of the non-deep learning baseline, and we previously established a bidirectional GRU model is one of the popular RM architecture, was very competitive in all the RNN models, and we show that augmenting the bi-GRU by Med-BERT is equivalent to, for some sample size, boosting of 20% of AUC area under the record. That's a prediction benchmark. Or put it in other ways, equivalent to increase the sample size for about 10-fold. And this is also true for other data sets, in this case, in proven claims data, other tasks like pancreatic cancer risk prediction, and some other architectures like retain. So how does exactly work? Just go back a little bit. When we're talking about the embedding, this is the idea. It just for any medical code, we first in computer represent it in so-called one-hot encoding, where the entire your alphabet, and then the item that's corresponding to this code is one, otherwise or zero. So that's how computer represent this code. It's sort of simple, but it's not very amenable for downstream neural network. So what in neural network typically we do is we translate this by multiplying by a matrix and into some x-dimensional vector, and this vector hopefully capturing the meaning of the thing. And this notion for embedding or concept embedding has been used in natural language for almost all their models. And so we adopt the same thing for this house EHR concepts. And the main requirement is we'll want the similar concept to be mapped to a similar vector, right? And that's why we're capturing the similarity of the concept. But also in word embedding, it shows even the vector from one concept to the other also have a meaning. It can encode in some semantic informations. So that's about the static embedding. What conceptualized embedding does is recognizing that same word, same token in different contexts may means different thing, right? For vomiting in the context of cancer and vomiting in the context of pregnancy means different things, right? the traditional static embedding would embed same word into same vector, which is not capturing the context. So BERT model is one of such based on transformer that can capture the contextualized embedding. Again, the machinery for statistics embedding is we have this token and embed into use embedding metrics and into these things, and we also for tokens in the same visit we aggregate that, but those are technical details. And the static embedding was shown previously is working, including some of our own work. But for contextualized embedding in EHR, we are one of the first to do that. The architecture basically, for the input, we first having layer for static embedding, and then in addition to the code static embedding, we also add a serialized embedding representing the sequence information, and also the visit embedding, including some sort of semantic unit. And then we basically embedded the code, the serialized number, and then the visit all into some vector and then add them up. So that's how we calculate it. We follow mostly what the classical BERT model have done. And the BERT model, I just checked today, it's one of really the probably most cited paper of all times. Notice only 4 years, it has been cited for 50,000 times. It just completely transformed the field of natural language processing. And really the idea is that it stands for bidirectional encoder representation from transformers, but what really does is capturing the context information for each code. Once you can train such model, BERT model, in a large text cohort or large EHR model, you can use that to fine tuning in your little data sets. That's the concept of pre-training fine tuning has been the revolutionary concept. So we take the architecture, we take the concept, but we train this model from scratch, from our own data. We did a little tinkering of the how to input embedding and what's the pre-training task to make it working. So for pre-training, we use the certain health facts, like I mentioned. After the cleaning, removing some errors and patients with very little sequential information, we end up with 28 million, and we inject some order in the data by including this priority, diagnosed priorities, or EHR billing and stuff. And for the pre-training task, basically BERT using the so-called master language model, we follow that, and we also add a classification task to predict the length of stay, so sort of the basic long hospital stay or not for the patients. And these are hyperparameters we use, not that important. And then a little bit of description of cohorts. The 28 million break down into I think some sort of typical United States sort of demographic distribution. And for the fine-tuning task, we use diabetic heart failure, pancreatic cancer risk in in Cerner Health Fact, this is the EHR data or the proven the claims data. So again, we after we train the thing, we attached it to a RNN model just because we have one handy, and we mostly evaluate the performance by how well the model do in terms of the downstream task. So here is what shows. We compare with like the BERT model, and then the model with static embedding is one of our early version, and then the contextualized embedding Med-BERT. So for each of architecture, we do this, and basically we show that in every case, using pre-trained Med-BERT would boost the performance and giving the best results. Even so, we use, I mean, if we don't use very fancy predictor, even very simple fully connected layer still show a decent performance. And that's little figurative result about the same thing, but our Med-BERT augmented model always fly higher in all cases. And one nice thing about this transformer model is we could visualize the attention patterns. So internally, in each layer of the transformer, there's a multi-head attention. We pick some head and then visualize for this token, what are the attention weights from the other code in this patient. So we see that in this example, the abdominal pain, other specified site, multiple sites, sort of jargon, but it is receive attention from chronic pancreatitis or acute pancreatitis, so sort of makes sense in linking the relevant term together. Another one for type 2 diabetes, we see it is pay attention to long-term use of insulin, not only within this visit separator, so it's also pay attention to the same code from previous visit. So that's the quick rundown of the Med-BERT model. Maybe I'll keep going to the end. I can answer more questions. Okay. So I'll dive into CoVRN, a recurrent neural network model for predicting outcomes of COVID. We did this work it actually at the beginning of the pandemic. I know it's sort of maybe more relevant to this audience, but it's just little as a review. Because the COVID pandemic is running so fast, we are, I don't know, maybe number 5 wave or so. It sounds like it's ages already. So we started the project around the first wave in 2020. Cerner at that time they are promoting their new cloud-based resource. They call it Cerner Real World, and then they share their COVID data to some 30 groups in the United States, and we are one of those. We follow their data release, and we use the cutoff at the end of September 2020. And we thought the COVID is probably gone, but it's hard to predict. We even at this cutoff, there were a lot of data, and we built a model and then read a paper, and then eventually published a few waves after that. So what we did was basically a recurrent neural network, and we have developed a GitHub repo called PyTorch EHR in our group, and also we share to the world. It's make building such model much easier. So in this framework, PyTorch EHR, we use PyTorch, but methodologically we use this notion: patient is a sequence of visits, and we just take in all the information within each visit, and we in the end make a prediction. Can make two kinds of prediction: binary probability, basically yes or no, in hospital mortality, mechanical ventilation, or prolonged stay, or we can make a survival prediction. It can be in hospital mortality, the time to event, also the time to event for the mechanical ventilation. And we choose to make the prediction at the time of admission. So that way, and if indeed this model was deployed, we can help hospital to prioritize patients, and so that it can tilt their precious resource to more relevant patients, right? And here is the data we used in Sonar real world data. Contains some 500,000 people, 500,000 COVID, and from 85 hospitals. And we split into training and validation, and then have the fine-tuned set that later we can evaluate in the test set. So in this Sonar real world data, we have these are the training, mostly training validation called super training set, and we also have multi-hospital test set that's distinct from those. And so we carve out 2 hospitals. We want to interpret how well this can be done in an individual hospital. And in the Optum, which is different data source, we got we use a part of the Optum data to fine-tune this model developed at the Sonar data, and then evaluate on held out Optum test set. So by doing so, we can evaluate the transferability. So here's the patient's breakdown, and basically it's the usual, not too much to be noted. And then these 2 data sets are sort of similar, but I would say Sonar data has I mean, less in hospital mortality and less ventilation, so they're slightly less severe, but more or less it's sort of similar thing. And the performance of our model after all the hard training is that we are glad to see the most part on the 90s, For the multi-hospital test set, even logistic regression, simple model can deliver 90, but our model RNN, both binary or survival is this number is for the C index. So we see its RNN model outperform simple non-deep learning model, but sometimes not by too much, more or less. It is better. We know in this game, better is better, right? It would help if we scale up, it can help a lot of patients. For mortality, for ventilation, for prolonged stay, and we all deliver decent results. And here's a visualization. If the prediction of our model be used to stratify patients, then we can separate patients according to their risk score into 3 bins, and then see they are pretty well separated, meaning that we could use it for sorting patients for the hospital if needed. And in terms of age group, we see the prediction is better for younger age, and depend on comorbidity, but more or less not too much different, and it's sort of similar across US census regions and the race as well. So for some race, we have limited data, so it's sort of make it less reliable. Also, if for real world deployment, we'll see how the model can be calibrated. We see it's overall pretty well calibrated, meaning it's the predicted value and then and a fraction of positive are very highly correlated along that diagonal line. So in conclusion, we show, I mean, it's a sort of a general term conclusion. We show when we have EHR big data, it's possible to use them to train a big model. And when the data is big enough, the big model will outperform small models. And it's possible we can train a contextualized embedding model from EHR data. And then using the pre-training fine-tuning paradigm, we are one of the first to show it is actually working for EHR data. That hopefully open up the possibility. We are looking for ways to share our data, but not today yet. We hope like in the near future, we have a version of the Med-BERT model trained on a different data source. Not Cerner, but a different data source could be shared, and that may help hospitals everywhere. And we show big models are transferable. We show the COVID RNN model trained on Cerner can be transferred into Optum, and also it's portable, meaning that if may not be immediate, maybe need some engineering, but overall, our model require somewhat minimal pre-processing. We take the data of fire host from the EHR, we attach to that, and we can make predictions. And if you have EHR in a similar format, we can more or less move one from one hospital to the other. So, and lastly, just shamelessly show our Med-BERT repo. Since we started about 2 years ago. It's been, I mean, less than 2 years ago. We've been enjoying some popularity, and I just want to say we hope to share that pre-trained model in the near future. And thank you for your attention. And that's the end of my talk.
Okay, thank you so much. I think I've learned a lot. Yeah, any questions from anyone, Emily or?
Yeah, I have some questions.
Yes, go ahead.
Thank you. No, that was really amazing.
Yeah.
Very applicable to some of the work that Amanath and I are trying to do at the moment. Really interesting.
Yeah.
I guess just so I'm not a computer scientist, like just, I'm a public health person. And I work a little bit in the computer science space, but I guess one of the things I was wondering around in terms of that training data, I know you gave some of those breakdowns in terms of you did have some of the racial information, but then you mentioned that some of that was, I guess, not as complete. So I guess I was just wondering about if there'd been any analysis on the representation of the training data. I know that doesn't necessarily affect the algorithms in internal sense, but in an application sense, there can be biases in prediction. So I was just curious about the analysis of the training data.
Okay. Yeah. Well, really good question. I mean, this is largely transparent from our model. We just take in the data, whatever we have. I think we are in the early stage of development. We just try to build the best performance model, right? But true, I think it's carry the same bias come with the data. If the data is biased, our model is biased. But I think maybe this slide is somewhat relevant. We didn't really plot what's the composition of this regions and age distributions, but it is to say our model doesn't perform equally across our group. That's just the way that the training data. Maybe for some group it's harder to predict, or maybe because some group the lack of sufficient data. But yeah, at least we just show that that's what we have. I think it's a lot of opportunity to mitigate the bias and make it model more equitable.
Yeah, and you're certainly not alone. So our EHR data is not representative at all. So Amanath and I are talking about doing, some work in this space, and we would be coming up against exactly the same problem, that we'd be working with data that's not representative. I think one of the really good things about this is the minimal analysis of pre-training data, because again, similarly, our EHR data is a mess. Like, there's so text heavy. So I think that would be a real benefit for us in using these methods. I did have one, and this is my complete lack of understanding of computer science, but if we're going to use this in another context, so obviously if we're using it in like an Australian context, there were different populations. Would we need to retrain on new data and just use the underlying principles, or how would that work?
Yeah, I was going to ask that question.
Yeah, well, so in this paper we did do pretty thorough sort of this transferability analysis, So we basically here in Cerner, even though it's one bigger house company, they deployed in different hospitals. They have a categorization, so it is not the same, right? But we see that the model trained on a bunch of 85 hospitals. They work pretty well for the other two. And also Optum is a claims data. It's a medical claim. It's not like a EHR where you just those numbers running within the hospital system. It runs through the insurance, right? And we show that even though they are collected in very different fashion, the model performance can be somewhat translated. So let me see. Yeah, we showed, I mean, the number from, I mean, it is somewhat different. Some hospitals are easy, some are harder, but the up and down. And then for the, let me see, where's the Optum data? Maybe in the next one. Oh, I may not include that, but in Optum, the numbers are sort of grossly similar. I think I forgot to include that slide. Yeah, you can read the paper. That's all we can say about the transferability on this.
Yeah, okay. So we need to test it really, is what you're telling me.
Yeah, I mean, at least the model itself is portable. You know, you can move it from one hospital to the other, and it can run. And then, but transferability means you act not only port it there, but also hit the ground running and producing good results. I think that's not having automatic. You will need to a little bit fine tuning.
Yeah. Sorry. In this example, when you say like multi-hospital and hospital 1, hospital 2, like, is that something like how does that work? Like suppress and tests in different hospitals, or is it like hospital 1 and hospital 2 are independent?
Yeah, those are two different hospitals among 87 hospitals in center data. And yeah, we just at beginning held them out, and so that we can do the evaluation without it contaminating.
Yeah. One thing I missed is like in the original data, like is the embedding only for textual data?
Oh, good question, Amina.
Yeah. We are using the EHR data. I mean, I think there are actually mainly two kinds of data. EHR, one is so-called structured data, or those data running in the tables, relational database tables, and another is called unstructured data, which is text, right? Including physician's notes and even imaging or EEG or all those kind of unstructured data. So
not
here,
not CT scans, or not images, or not videos.
Those are unstructured. All we talk about today is about structured data.
Okay.
Yes.
I do think in the EHR context, though, so if people had a scan or something like that, then there would be a text report generally attached to that as well.
Okay.
So it wouldn't be as important for this kind of analysis, I would suggest. And sorry, I have just one last question. I'm so sorry, this is my last one. Do you have any plans to implement this? Are you working with anyone to see how it will run in practice?
I'd love to. Nobody reached out to us yet. I mean, frankly, I think this model shows working at this stage, right? But now we are a few waves after a lot of vaccination and population immune stuff happening. I think it's probably the relevance of the model is reduced. I wouldn't just blindly deploy the model in the hospital. We want to retrain it and then sort of make sure it is well calibrated and then making good prediction before we can deploy it. But I think a general methodology should work.
Okay.
Thank you. Sorry, so many questions.
Okay, good question. Thank you.
Yeah, anyone else? I do have one question. Are the slides available? Like, if I email you, like, I'd like to go through the coordinates.
Yeah, of course. I'd love to share it.
Yes, thank you.
These are all published results. I mean, it's in the paper too, but of course, let's share.
Yeah, I think Amanat and I will definitely be looking up your paper.
Yes, and also like the codes as well, like it will be good to understand.
Yeah, and for both papers, we have a code repo. I think its link is in the paper too. You check out. We love to share our source code, and even hopefully we can share our pre-trained model. I think the COVE RNN pre-trained model are available, so you can just download it and play with it with your own data. For the Med-BERT, we are working on hopefully share that the pre-trained.
Yeah, thank you. Yeah, does anyone else have any other questions? Yeah, I think I think that's it from the audience. I really enjoyed the talk. Yeah, it's so informative and relevant to the work that I'm doing. Okay, once again, I'd like to thank you for your time and all the preparations in this presentation and joining us. Okay, and I'll definitely keep in touch.
Okay. Well, Ms., thank you for the invitation again, and thank you for attending. Well, have a good rest of your day.
Have a good day. Thank you.
Thank you.
Thank you. Bye-bye.